C'est bon? Bonjour. Welcome back to QX01, Introduction to Quantum Information and its Associated Technologies. So let's have a look at what we've covered so far. So far we've seen introduction to the subject, and then we also looked into the classical information and computation side. And we started last time to introduce the qubit, which we are going to develop more today, and perhaps starts on the notion of multiple qubits and the very important notion of entanglement before carrying on to other concepts. So this is what we're going to cover today. So I'll go back quickly to what we've seen already on the difference between bits and quantum bits. So we talked about the mathematical representation, so I'll go back to that, and in particular, a nice geometrical representation of a qubit, which is called the block-sphere representation. And then I already started to introduce the example of a simple qubit, the photon, and for that I will show you a typical experiment of what we call quantum optics, and how we can use photons as qubits. And then I'll finish this part on the dual space of a ket being these sort of weird vectors we've seen so far, which is called a bra, which is can be seen as a dual qubit of a ket, and we'll see why this is important for the following. So before that, just a quick note I added. So today is the 8th of March, and so it's International Women's Day. And so when I did the two brief histories of quantum computation and classical computation, I could have mentioned that there was at least one lady that contributed to the subject. So this lady is Ada Lovelace, so British lady in the 19th century, and as far as we can tell, she would have been technically the first computer programmer because she used the so-called analytical engine at the time in 1837. So she used the concept of such a machine, a mechanical computer that was devised by Charles Babbage. And this complicated classical computer, mechanical computer, had everything that was necessary to make computations with complicated gears, and complicated gears, and then more gears that were linked with each other. There was also a long right-hand side here of this computer, this engine, that was used as a memory. So there was all the components were already there. And what this lady did is that she, using this machine and how it worked, she effectively ran the first algorithm, known algorithm, to run Bernoulli numbers on this analytical engine. So I guess that was as I said, the first computer programmer known in history. So I think I'll remove, can I remove this? No, I can't remove this. So if I go back to what we've seen last time, so define a qubit, so quantum bit. So there are different notations. So usually we like to use psi, because of the physical meaning to it, but computer scientists and mathematicians would just use Q, for instance, for qubit, whatever. And we said that a qubit can be seen as a 2D vector with two components, so the 0 and the 1, and coefficients, alpha and beta, which are particular coefficients in the sense that these coefficients alpha and beta are complex numbers, first of all. And second of all, we like to work with normalized quantities, so normalized vectors, which here we called kets. So that means there is a relation between alpha and beta, which is that alpha squared plus beta squared equals 1. And of course, so this state is the equivalent of the 0 state for a classical bit, and this one of a 1 state for a classical bit, with the difference now that the quantum physics allows you the so-called superposition and the existence of both states at the same time. So we've seen, we made this parallel. We're going to use again today that qubits are effectively vectors, so they can be seen as 2D vectors, So we could write it like this, and like any vectors in the standard sort of Euclidean coordinates, it can be in a road. Any vectors can be seen as a linear combination of the two vectors in x plane. And in our case, so we have the equivalent here. If I introduce a sort of intermediary notation, which would be something like this, but as I say, for practical reason, Paul Dirac introduced much more useful notations, the so-called bra-ket notation, and we're going to see the bra part of it today. And from then, so those are 2D vectors. Therefore, that means that so this ket psi is qubit, can be written as alpha 1, 0 plus beta 0, 1, where this would be the 0 vector and this would be the 1 vector. So this ket is effectively a column vector as opposed to a row vector, which we're going to see today, which is the equivalent in the dual space of the bra counterpart. And so this is the ket, and we're going to see the equivalent in the dual space, which is the bra counterpart, which we write in the inverse way. And as we've seen, we can have, so of course we can go from one qubit to another or one vector to another using rotations, for instance. So that would be the rotation matrix in a 2D space that we know. But we would have the equivalent in the such space. Except that what we're going to see is that these matrices for quantum information gather particular meanings because, first of all, they have to be physical. I mentioned that, and I'll come back to that, as in they have to be related to a physical quantity, a measurement, first of all. And second of all, then these matrices can represent the quantum gates that will be manipulating the qubits. So the three matrices that we, as examples, that we're going to use quite a lot are the so-called Powerli matrices. So there are 2x2 Hermitian matrices. So they are sigma 1, sigma 2, and sigma 3. Plus, if we add the identity matrix, and these four matrices actually form a basis for any 2D matrices in a particular space. And these matrices, as I said, in order to represent the physical quantity, a physical meaning, because at the end of the day, this quantum computer is based on physical components, they have to have this particular property of being Hermitian. Hermitian means what? Means that the matrix has to be equal to itself, but with the a particular operation which we call a Dagger operation. So we have to have Hermitian matrices, which means that a particular matrix A has to be equal to A dagger, where A dagger is the dual transformation of complex conjugated and the transpose. And we've seen an example on sigma 2, where we take the complex conjugate of, so for is easy, it's themselves. And then we take the transpose, so the symmetry part along the diagonal lane of the matrix, and we end up with the matrix that we started from. Okay. If that is the case, and we have a Hermitian matrix, and that's very important, as we will see later on, because these mathematically represent as a physical meaning in the physical world by the base of a control or a measurement of the qubits. One more thing we said also is that there is this particular sign on top, which we call hat. It could be anything else, but we use that hat notation to signify, again, that there is a particular meaning to these matrices and that they represent physical quantities. Right. And then we said that, for instance, the sigma 1 Pauli matrix and in particular instance is the NOT gate that we have in classical computing, because the Pauli matrix, as we will see, as you can already see here, just invert your 0, 1 vector with 1, 0 vector. Okay, so we just reverse the qubit, like in the classical case where we would reverse the 0 into 1 and the 1 into 0. Here we do the same, except that we keep the superposition. Okay. We'll see that later on. But basically, we have our first quantum circuits. So these are the 3 quantum circuits associated to the Pauli matrices. So X, Y, and Z correspond to the sigma 1, sigma 2, and sigma 3 here. We also have the identity matrix, which we usually do not write like this. We just say that it's a wire into our circuit. And if I have my first quantum circuit, then I start with the qubit phi along this circuit, and I do a quantum gate here, a specific quantum gate, Pauli matrix X, and I end up with phi prime, and this phi prime will be the output qubit, which in this case will be the reverse qubit of the one we started with. Okay, so if I do it quickly, psi prime would be the X matrix. So the X matrix is this one. So 0, 0, 1, 1, 0, and I apply this to this generic qubit, which I can write let's write it like this. All right. So 0, 1, 1, 0. So I can rewrite it like this. So 1, 0 plus beta 0, 1, 1, 0, and then 0, 1, if I write in terms of a vector column, like so. So this will give me the vector 0, 1 plus beta 1, 0. And this is exactly 1, and this is exactly 0. So we did indeed invert the 1 into 0 and the 0 into 1. Right. So this is our first quantum circuit. So of course, what we said is that this can be seen as a dial. So that means that depending on the coefficients alpha and beta, I can go from 0 to 1 and then use any combination in between. I can also have a phase here. I can have an I because alpha and beta are complex numbers. So they're normalized. So this would be the normalized vector. And if I have complex numbers, so I could have an I here or any possibilities that has this property of having alpha squared plus beta squared equal 1. The most used qubit is the one that is 50-50% chance, where you have 50% chance of having 0 and 50% chance of having 1, although in some algorithm or some specific circuits, you may want to use a different weight, depends on what you want to do. But this would be the more general state. And we made the link with the so-called Schrödinger's cat, if you remember. So quickly, we said also that we can have a geometrical representation of such a qubit. This is the so-called block sphere on the right-hand side. So this is the classical spherical coordinates in classical mechanics. But there is a direct automorphism, direct transformation to go from this to this, where this now can be seen as a sphere again, but a sphere that gives you basically all the pointing possibilities of the vector. Okay, so any qubit, so depending on alpha and beta, so any values, continuous values that alpha, beta can take, you will be able to represent the qubit associated to it on this sphere. So there are particular points. There is along the North Pole and the South Pole, which would be the 0 and the 1. You also have along the equator. So if you are along X, you would have the diagonal, anti-diagonal, so 0 plus 1 and 0 minus 1. And if you are along the Y direction, and the specific direction along Y, then you would have 0 plus I1 or 0 minus I1. Okay, and the general state of this alpha 0 plus beta 1 can be written like so for a qubit, where you have theta and phi, the two angles here that we see again in this representation. And I gave you an example here of a particular qubit and what theta and phi have to be in order to get that qubit. Right. And then so we're going to come back to that and with some demonstration. So I told you I'm going to use two physical systems quite often. The others will be mentioned, and you will see some of the technologies like superconducting qubits or trapped ions. That would be much later on. From time to time, I will use two specific systems, physical systems, to represent these qubits. So the first one, and the one I will be using the most, will be the photon as a qubit. So a quick reminder, a photon is a particle of light. Light is an electromagnetic wave that is governed by the so-called Maxwell's equations, which are on the right-hand side. In vacuum, in space, you can show that this Maxwell's equation can be written like so, in a so-called propagation equation, which is a standard equation in wave physics, actually. And this propagation equation is for the electric field. And what we said is that there is a nice property of the electromagnetic field is that so an electromagnetic field is made of three components. So its direction, u, and it specifically is wave vector. So the wave vector k is actually 2 pi over lambda, where lambda is the typical wavelength of the wave. So it would be the same for a C wave. You would have the same characteristic. And then what you have here for a particular electromagnetic field is that you have basically an oscillation and an exchange of oscillation between the magnetic field component and the electric field component. But as I said, the good thing about electromagnetism and Maxwell's equation is that you don't have to worry about the two components. You can only you can only use the electric component, for instance, as a characterization of the electromagnetic field. Okay, this is enough to fully represent the electromagnetic field. And so therefore that means this propagation equation is basically enough to characterize the propagation of the wave. So that would be for light. But what we can show is that, and we're not going to do it, but that Maxwell's equation can be quantized and can therefore explain the notion of photons. And the good thing is that photons will follow exactly all the same properties. So even a single particle of light will follow all the same properties as the electromagnetic wave counterpart. In particular, light is polarized. So that means photons will be polarized as well. And as we said, and we're going to see that today, we will use that polarization state precisely, or it's one way of encoding information onto a single photon. Okay. And typically, so if I go back to the propagation equation quickly. So what we said is that a typical solution of a propagation equation is a plane wave. And it's, in fact, good enough for a lot of problems in electromagnetism. And so if I have a propagation along the z-axis, typically, so propagation along the z-axis. Oh, that's another thing, by the way. So I will never say the z-axis. I will always say the z-axis. So along the z-axis, then so this would be the most general propagation equation. So 1 over c squared. So c is the speed of light in vacuum. E is the electric field, but in this case, it covers the entire electromagnetic field. And then I have second derivative in time of the electric field. And so a solution of this equation is a plane wave. Okay, so as we said, so typically something that will look like this, something you can see here, something that will oscillate in space and time. So if I write it, well, I can leave it like this, so I can use also a complex notation, it's the same thing. So I have kz, where k is the wave vector, and the characteristic of the propagation axis of the wave. Oops, sorry, too fast. And then omega is the frequency, and is related to the wavelength. So I remind you. So we have lambda equals c times t, or 2 pi c over omega, for omega is related to lambda. So if I have only one dimension, this so-called D'Alembert equation is, so if I remove the vector dependence, then all I have is a dependence in z only. Okay. So if I derive this twice, according to z, then what I'm going to end up with is minus k squared e. If I derive it once, I will have a minus k sinus, and then if I do it again, I will have minus k squared times same quantity. And on the other side, I will have minus omega squared over c squared E. Okay? And what I derive is the fact that a plane wave is solution if I have this particular relation between the wave vector and the frequency, which I can rewrite like so, as being 2 pi over lambda. Okay. So this is so-called in electromagnetism the dispersion relation, but whatever. So that's that. And then what we said is that the vector component of this plane wave, so this vector here, the orientation of the electric field, basically characterize the polarization of light. Okay? And as we can see here, that means that typical polarized light can have two components, so one along the x-axis or one along the y-axis. Okay, so it can oscillate. So if the wave propagates towards you, so z propagation, it can oscillate along x, so that would be a linear vertical polarization, or along y, and that would be a linear horizontal polarization. Okay. So if I write this geometrically, I've got dependence along x, along y. Of course, I can have a diagonal polarization. So if I sum the two, so then I can have, as the wave propagates towards you, I can have oscillation like this. That would be actually diagonal, yes, or like this. That would be anti-diagonal. I can also have a phase between one component and the other one. So this phase here, pi over 2. And therefore, what I can have now is a circular polarization. So it could be circular right or circular left. So it would be like a helicoidal movement for the E field towards you. And what we said is that the good thing is that if I apply this to a quantum object, this is a classical wave, but the quantum part of this classical wave is the particle object, the photon. Then at a single particle level, then I would have the same thing, because now I can say that these two states could be my 0 and my 1. So it could be my 0 qubit, my 0 state, or my 1 state. But then we see straight away that when I'm diagonal and anti-diagonal, then basically what I have is an equivalent of a superposition between the 0 and 1, because well, basically I have the projection of the vector along x and along y. So that would be the diagonal state. I can write like this. And if this is 0 and this is 1, again, taking this vector analogy, then basically this can be seen as, if it's 50-50% chance, then a sum of 0 plus 1. Okay? And then here we go. This is already an example of a qubit, of a superposed state between 0 and 1. And this can be seen as a particular qubit where alpha equals 1 over square root of 2 and beta also. Like I said before, in the circular polarization state, then we have the same thing, except that now we have a phase I that is introduced along the way. But again, this is also a qubit. Okay. So polarization state. So let me show you. So I brought some things. So first of all, let me show you the polarization effect. So here, what I have is just an LED. And I have two linear polarizers. Okay, so an LED light typically has no particular polarization state. So what I'm going to do first, so that means it's a mix of all of it. So what I'm going to do first is, first of all, have a, sorry, I'm just going So first of all, I'm going to polarize light. So I'm going to put this polarizer in front of the light. So that means that the light that will go through, so some of it will be blocked because it has the wrong polarization. Some of it has the right polarization and will go through. And then I'm going to use a second polarizer that I'm going to put in front, and I will rotate it. And typically, so these two they're equivalent, and typically they have a specific linear axis. It's a linear polarizer where the light can go through. So that means that when these two axes are parallel, then it's almost like I didn't put anything. But when I will rotate the second one to orthogonal polarization, then I should see nothing, right? Because only one specific polarization comes out from the first one. But then I cut it with the second one, so there should be none. Okay, so first of all, I put the first one, so no, there is less light, of course, because some is blocked, but there is still some. And then I put the second one, so I can see there is also still some light. And now if I rotate the second one, so I go from a maximum to a minimum. And eventually here, I'm at a minimum where there is nothing. And that's because I cross-polarized the two polarizers. So what I did is I first of all send a specific state, polarization state. So this works with light, but if it were to be a single photon, it would be exactly the same thing. So a single photon would go through the specific polarization, say 0, and then I put a second polarizer, and I can block this photon, this qubit, by cross-polarizing the two polarizers. Okay? So this is what we would do typically. There's another example of this very nice crystal called calcite. And this, so I don't know if you can see, so there is a cross here. And this particular crystal has the property, as we'll see later on also for other optical components, to separate polarization states. So what I'm going to do is I'm going to put this on the cross. And if I am along the so-called normal axis of the crystal, then I should see the cross in a normal way. But when I will rotate the crystal, then I will basically split. I will start to see a double cross and split the image into two. That is not because I split the image into two, or it is, but I split it in polarization. It's because now I separate the two polarization components of the ambient light that is shining this cross. Okay, so let's have a look. So here is the first, I have to see, voilà. Oh, here is the first state. Sorry, let me put it. Voilà. So here's the first state. So there's only one line, and then as I turn it, then two lines appear. You guys can see after. All right, so I cross it. So this typically, this is what we call a birefringent crystal. It's used in optical components to control the polarization state of the light, or to separate the polarization state of the light for classical light, like this one, but also for single photons. So now, if I go back, so typically, here is a nice representation of the different polarization state. So here, it would be the vertical polarization state, this wave going towards you. Here, likewise, except that now the polarization is along the horizontal axis. This is the diagonal. So in blue is the diagonal component, which is the composition of the two, and we can see, so at 45 degrees. And then here would be what it looks like typically on a circular left and circular right kind of polarization state. So the good thing is, as I said, so photons will follow the same rules. That means the good thing is that I can use standard optical components, so like so. So those would be standard optical components, which are, we've seen an example, so polarizers and various plates. And so typically what we have, for instance, so give you some example, we use in the lab what's called a half-wave plate, also called a lambda/2. And that specific crystal the specific piece of glass, will rotate a linear polarization state to another one. So basically, using this half-wave plate, so depending on the rotation of the crystal, you can change a horizontal state to a vertical or to a 45-degree diagonal state. If you use this one, which is a quarter wave plate, also called lambda over 4, that what you do is you transform a linear polarization into a circular polarization. Okay. You also have other components, like the one we're going to see in a moment, which are called beam splitters. So beam splitters are two kinds. So what they do, they split the beam. And they are of two kinds. So you can have a non-polarizing beam splitter. So it would be something that would just split the light 50% left and right. As it is already, you can ask yourself, what does that mean to split a photon 50% left and right? Okay, so we will think of that in a minute. Or you can have also what we call polarization beam splitters, which would be these nice cubes. And what they would do is they would do the same. They would split the light into two directions. So usually one is transmitted and one is reflected. But they would separate the light depending on the polarization state. So for instance, in this case, the horizontal polarization would go through, whereas the vertical polarization would be reflected. So again, we can see here why photons as qubits are very interesting, because if we can apply these components to light, to photons, that means we can control the states of light. We can separate, so H and V now, if H and V are 0 and 1, then we can separate qubit states, we can recombine qubit states, we can transform qubit states to make gates, and so on and so forth. And by the way, this is one of the features of quantum mechanics that you must have heard sometime in your life, is the fact that in quantum mechanics, any particle is what we call the wave-particle duality. So any object can be seen both as the wave and as the particle. I'll give you an example later on, again using light, a true example of this behavior. And you may have known the so-called Young's slit experiment, where you send a beam of light through slits. So in this case, there are 3 slits. And what you end up with is some interferences between the waves. So that perfectly explains for wave physics. So you would have the same if you use sound. Now the real question is, what happens if I attenuate the light enough to send one photon at a time? Okay, and what you can show is you have similar behavior in the sense that all the photons somehow will end up in this particular pattern, interference pattern, when you do the experiment many, many times. Okay, and that shows that there is a duality, the dual character between the wave part and the particle part of any object. And this is, again, at the heart of quantum physics and therefore at the heart of quantum technologies. And nothing to be afraid of in classical, in the standard quantum mechanics. It makes perfect sense. Yes? Good. Okay. Right, sorry about that. So as I said, what was here was a Galton board, and I'll come to that later on. So as I said, now what we can do is have a single photon now at the single photon level, and then send it to all these optical components that I showed you, and therefore being able to do quantum gates. So these would be the equivalent, because those operations that you can do a polarization state, as we will see later on, can be seen already. We've seen one of basically inverting or transforming a qubit state into another one. So using this complicated optical setup, we can actually control qubits. So what I brought here is to mimic such a system. So I'm going to show you how, what it would look like if we were to have a true single photon source. So here, of course, it's mimicking in the sense that what I'm going to use is a laser. I'm going to use a polarizing components, and I'm going to use 2 detectors and a polarizing beam splitter. Okay, so let's have a look. So what we have here is, I think we need to zoom, please. There we go. So what we have here, so here is the sort of single photon part, so is the emission part. In this case, it's not a single photon source, it's a laser, which is here. Here we have the polarizing component that's going to change the polarization state of the laser. Here we have a polarizing beam splitter, so it's a cube that can split the light depending on the polarization state. So one would go through and one will be reflected. So those 2 are the 2 detectors, and basically when the light goes off, that means that there was a detection of light. Okay. Okay. So this laser is already polarized, so it's in a polarization state. And now, right now, what we have is the plate to let the polarization go through the plate. So if I press this button, then I'm going to see the blue light here. That means the photons, so say they are vertically polarized, they go through the polarizing beam splitter and they end up in this detector. Okay, so if I do it again, then it's end up here, and I can do it again and again and again. Okay, so if I were to have a single photon, typically, even a polarized single photon, typically that's what I would have. I would have a photon coming out of my source. Here is not a single photon source. Again, it's a laser, but it's the same idea. And then it would go through the polarizing beam splitter and be detected by this detector. Now what I can do is I can rotate this component and go from this state to this state. So now I should have detection on this side. So if I look at here, indeed, I have detection on this side. So the photons are now in the other sort of qubit state, the other polarization state. So they went from 0 to 1, and is detected on this detector. And I can go further. I can now set this polarizing component to being 45 degrees. So what it means now is that the light that comes through is at 45 degrees. Okay? So if I were to have sort of standard light, so a proper laser, again, this is mimicking a single photon source, but if I were to have a normal laser, not mimicking a single photon source, what I would expect is, as I have the 2 components, I would expect the 2 lights to go off. In this case, what we did is we added a trick so that we mimic a single photon. And what does that mean here is that a single photon indeed cannot be split into 2. Okay? So it means what? It means that when the single photon arrives on this polarizing beam splitter, so in a 0+1 state, in a diagonal state, it will trigger only 1 detector. Okay? It cannot trigger 2. It cannot trigger 2 because there's only 1 particle. So the particle is either there or there, but it cannot be in both at the same time. If I were to have many, many more photons, then yeah, sure, I can split them into 2 groups. Okay? But for a single one, this is not possible. So what I expect, indeed, is to see a probabilistic way of detecting my photon here or there. And as I'm at 45 degrees, we saw that this is typically the same weight, so 50-50 chance. That means that, I don't know in advance, but in 50% cases of the time, this detector will trigger, and the other 50% cases, this trigger will detect. Only one of the 2 will trigger, but in a random way. I do not know in advance what I'm going to get. The only thing I can tell is that if I do 100 measurements, on average, I should have 50 measurements, 50 detection on this one and 50 detection on this one. Okay, so let's have a look. So now I rotated it. So first goes off here, then goes off here, then here again, why not? And here, 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 oops, here, etc., etc. Okay, so if I were to reproduce this 100 times or so, then on average I should have 50 clicks here, 50 detections here, and 50 detection here. Okay, so that's what you would get with a single photon source. So one thing is that, so in this particular experiment, so as I said, is mimicking. So I actually use a laser, and there's a trick behind. But what we have to know is that a laser. So you'd say, okay, well, that's not a problem. You take your laser, and then you just attenuate it. Yes, indeed, you're right. We can attenuate laser. We can attenuate light, and that's what sunglasses do, for instance. Except that intrinsically, sunlight, laser light, do not have the right properties to provide us with a single photon at a time. Okay, this is what we call quantum optics, and we're not going into that because it's not the purpose. But just for you to know that we cannot just use any light source. So for that, we need a particular, what we call in atomic physics, or in physics in general, a two-level system. And a good example is, for instance, if I were to isolate a single atom, and if I can isolate two particular energy level of this atom, then this can be a single photon source. Okay, so atoms are quantized, so they can go from one level of energy to the next one, but they can only do that, so the electron can jump from one level to the next, or from the bottom one to the top one, say, and only, so the electron can go from here to there, and when it comes down eventually, it will release the energy that it absorbed by emitting a photon. And that is a single photon, because that is a single quantum of energy. Okay? And that's okay, because also this system now, if I want to re-excite it, as we use as a vocab, so to take the electron back down and put it back up again, then this cycle of up and down, releasing photons, up and down, make sure that you actually have one photon at a time. Okay, so people sometimes talk about a photon pistol. Okay, so photon gun, because every time you need the trigger to release the photon from one state to the other. But that ensures that you only have one photon at a time. If I use a laser, it's much more complicated than this. It's a collection of those, and it doesn't work. Okay. Right. And there are, as we will see, other systems, other physical systems, where we need such energy levels. So here I talked about atoms. So actually people do isolate single atoms into optical traps in order to do these experiments. And other people use trapped ions, which is trapping atoms but differently, or superconducting qubits using electrical circuits, or also electron spins, which is a particular property of electrons that we're going to talk about much later on. So that's what I wanted to say on the one physical system that can be used as a qubit, meaning a single photon and the polarization state of a single photon. We will use that again as a nice system, physical system, to understand some of the concepts. Now back to sort of more formal definitions. So I said that there is one aspect that we need to talk about is the so-called dual space of this vector. Okay, and in particular the dual state of these quantities that we define is kets. And those are called bra. Okay. So first of all, let me take a step back. So I don't know how you you used to learn vectors, and in particular matrix calculations, but if you learned it like I did, you learned it the wrong way. Okay. Same for the scalar product. You most likely learned it the wrong way. So what do I mean by the wrong way? So if I step back, so if I take two vectors u and v, and I want to get the scalar product, but we will call it the inner product, but it's the same thing. For what we learned is the scalar product. So most likely, or I don't know about you, but the way I learned it is so if U was, say, defined by two components A, B, and V would be C, D, then what we learn is that, well, U can be written in a vector notation, AB, and V can be written CD. And if I do the scalar product, what I do is I do this times this, plus this times this, but this is 0 because it's the cross scalar product of the, say, EX and EY vectors, plus BD, and CB would be 0. So what I would have is AC plus BD. Okay? So that's what you most likely learned. The second thing that you most likely learned is, and that is the proper way, is how to multiply matrices. So the way to multiply matrices, so there is an example here to multiply A and B. So we have A times B. And so what we wrote to say, okay, A is 1, 7, 2, 4, and B is 3, 3, 5, 2. Okay. And depending on how you learned it, there's a nicer way to write it. So if I write it, so to write it sort of shifted like this. Okay. And then end up with the C matrix. And what we did is we say, okay, I've got, as I multiply two matrices, n by n, then I should have an n matrix here. So the way we do it, so 4 components. So we do this times this. So what does that mean times? We say, okay, it's 1 times 3 plus 7 times 5. Okay, so it's 1 times 3 plus 7 times 5. Okay, so I'm going to have to get it bigger. For the second part here, it would be the same. This time it would be 1 times 3 plus 7 times 2. Okay. And then this part here, I've got 2 times 3 plus 4 times 5. And then this one here would be 2 times 3 plus 4 times 2. Okay? And that would be whatever numbers that is. And that would be C. Okay, so well, I can write it. That's, yeah, anyway, that's some numbers, E, F, G, H. Okay? And that's okay. But now the question is, okay, this is by 2 matrix. And what happens if I want, so vectors, as they're here, can be seen as just one, 1-2 matrix, okay? It's a particular matrix. So in other words, that means that in order to obtain this value, if I want to have the equivalent of matrix calculation, this is actually the wrong notation. Because effectively what I did here, and you can see here with the vectors A1, A2, B1, B2, is effectively what I did is I multiplied the vector A1, oops, which is, let's use color, which is this vector here times B1, which is this vector. But those aren't the same vectors, because this is, so this would be B1. So this A1, this would be B1. But B1 is, as we know it, a so-called column vector. Okay, it's written in a column. But A1 is not a column vector, it's a line vector. It's a row vector. Line or row, depending on, depending on the definition, the word you want to use, with the same idea. So, and same for the others. If we have A2, then this is this times this one for this part, and then this would be B2, and then we have A1 times B2, we obtain this, and we have A2 times B2, we obtain this. Okay, so we have A1, B1, A1, B2, A2, B1, A2, B1, and A2, B2. So that means that, again, I don't know how you learned it, but that means that in a way this was not really a nice way, or should I say more, not a nice systematic way of defining vectors. Because if we want the equivalent of that, what would be nicer is to say that U V is in fact the scalar product of a line vector times a column vector. Right? So it would be AB times CD. And that is the equivalent of the A1, B1 I have here, which I did, which I obtained by doing this times this, which is 1 times 3 plus 7 times 5. So here there would be AB times CD, so it would A times C plus B times D. So it would be AC plus BD. Okay? So this would be more the strict equivalent of that. And the reason why I do this is because this is very important in order to introduce now the notion of line vector or row vector. Line or row, depending, same thing but different. As opposed to this one, which is a column vector. So of course, what's misleading here is when we write it like this, it looks like we don't make any distinction, and yet there is a distinction. So depending on which side, there's a distinction. And in particular, in this particular case of the formalism we're going to see for quantum information, we need to specify the fact that the left-hand side and the right-hand side are not symmetrical. Okay? First of all, because, well, it's a line vector and it's a column vector. And second of all, because on top of it, we are, if you remember, in a particular space with particular elements and particular matrices. We talked about emission matrices. That means that on top of it, there is complex conjugated that come to it. So definitely the left-hand side and the right-hand side are not the same. Okay? It's also misleading when we used to learn it, is that if we do U times V or V times U, it's the same. Well, yes, it's the same, but that's because it's a particular mathematical geometry, Euclidean geometry. But in a most general way, in mathematics, you can have UV not equal to VU. Okay? Right. Okay, so what does that mean for our qubits? Well, it means that now I can define a scalar product that way. So if I go back to qubit notation, so alpha, beta, gamma, delta, so I would have this. And I can now transpose that to my qubits by saying that the left-hand side is different than the right-hand side. So the right-hand side would be sort of the standard vector. So this would be the column vector. But the left-hand side now is the row vector. So it's this one. So that's why, as opposed to here, we can put a particular sign. In this case, I put a particular sign, I put the transpose sign, right? Because, well, the way to go from here to there is to use the transpose operation, which is exactly the same as the transpose operation in a matrix, which consists in sort of flipping over the coefficient of the matrix along the diagonal. And here's the same thing. I flip over the column vector to the line vector. Equivalent, but in one. So that means that this actually should be defined in terms of qubits as this notation. So left-hand side, different than right-hand side. Okay? And those mathematically are dual to each other, with each other. So that's why this is the representation in the dual space of this. And the dual space is what? It's just simply going from, in this particular case, going from a column vector to a line vector. And now, we can use if we go back to these sort of weird notations, the bracket notation, then this, we said that this would be the ket notation, so we've seen that already. This would be the ket. And now I can define I have to define another quantity in the dual space, the left-hand side space, which is not symmetrical to this one. And I write it like so. So it's the equivalent of that, but flipped over. And this is what we call a bra. So why do we call this a bra and a ket? Well, because when I combine them together, when I do the equivalent of that, and therefore that, rather this, what I do is the scalar product. And what I do, which we call an inner product in this particular space, but whatever, we can call it scalar product, same idea. And when we join them together to make this operation, we form what's called a bracket. So let's get rid of that part. Oops, maybe keep this one. So now, so the equivalent of that would be the bra times the ket, which is basically to bring the two together. And we usually, so technically, we would have something like this, where we bring them together to make the scalar product, which we call the inner product. Okay. And this, so we could write it like this. But what we do is we get rid of these two lines and we just put one line and saying that this is like this. Okay. So this is the strict equivalent of that we know very well. Except that now we have to treat the ket part as a column, and we must treat the bra part, as a line. Okay? And we go from here to there by a transpose operation. Transpose and conjugate as well. Remember, the actual matrix operation is the Dagger operation, and the Dagger operation is transpose and complex conjugated. So in fact, here what's missing, and we will see, is we also have to do the complex conjugate as well. Right? So typically, the bra vector can be seen, as I said, at this notation as being the psi dagger, which can write it as psi is a ket in ket notation. So to go from here to there or there to here, we use the Dagger operation. So now is the difference with what I wrote here. Here was the transpose, but here we need to do transpose and complex conjugate. So what we need to do is the Dagger operation, here. Okay. So if I want to go from the ket psi to the bra psi, what I need to do is the Dagger operation, which is the complex conjugate plus the transpose like we saw earlier for the matrices. Okay? And this operation, this Dagger operation, will allow us to go from one space, so the ket space, to its dual space, which is the bra space. Okay? Or to go from the column to the row and back to the column. So typically, I have a non-symmetrical scalar product, as we said, and typically this is what it would look like. I would have alpha. So I can't see. Yeah, it's a star. So if I have, so let's do this. I need the. Now let's get rid of that and go back to bracket notation. So now if I give you two kets, I give you psi equals alpha beta, and phi equals gamma delta. And I ask you to do the inner product between the two. So I ask you to do this, so the scalar product in this particular space. Then what I have is on the right-hand side, I have the column vector, so that's untouched. So this would be gamma delta, sorry. But then here, I have the dual part, so the bra part, which is this, the daggered, let's say. Okay. And that is what? That is take this, transpose it, and complex conjugate it. It's not a word, it's not a verb, but it is now. So alpha star, beta star. Okay? I did the two operations. I transposed it, this one. So I transform into a line vector, and then I complex conjugate it. And the result now is this times this, so it's alpha star gamma plus beta star delta. Okay? Right. So I believe in mathematics, this particular form here is what we call a Sesquilinear form. And in fact, this is one example, but there are others. And in particular, there is one that we're going to see later on, which is the equivalent of the bracket, but using integral. Okay? So if you use integrals, so integral of psi star phi d tau, where tau is the integration of an entire volume, because again, this has to be some physical system behind, then this actually has a physical meaning, okay? It's still an inner product, so it's the same. It would have all the same properties that I just mentioned with the dagger, the transpose, but in the integral form. And this, to go from here to there, is basically to go from sort of quantum computing science to quantum physics. Because what the actual meaning, physical meaning of quantum physics, which again is not what it is about here, is given in this representation, as we will see later on. Right. Okay, so now we've introduced that. And now we can deduce a lot of different properties. So for that, just read the field manual. RTFM originally actually means read the field manual, where you would have many properties that would be the equivalent of what you have in standard scalar product in Euclidean geometry. So first of all, we defined that already. So we said that the bra is the ket that has been daggered. Okay, so this is equal to that. So if I start from this column vector, that's what we just saw, then I end up with this line vector. Of course, we can introduce a norm, the norm of a vector. So the norm of a vector would be, so the norm of psi would be simply that, okay, which is the equivalent of what you have when you do vector u times vector u, vector itself, itself. So the norm, we can write it like this, for instance. So that would be the square root of the inner product. And this has to be positive. This cannot be a complex number. This has to be positive. Of course, if the vector psi is 0, then I have a 0 norm. I have the null vector. So in the case of a qubit with alpha beta, we saw earlier, then what is the norm is simply alpha squared plus beta squared, and that is equal to 1. And we said we like to use normalized state vectors. If I have two vectors, vi and vj, then I could have a family of orthogonal vectors, the equivalent of what we have in Ex, Ey, Ez. So what that means is that if I take the inner product, the scalar product equivalent, then I end up with delta ij, where delta ij is 1 if I have I equal j, and I have 0 if I is different than j. Because if basically I have orthogonal vectors, then the scalar product would be 0. Again, at the end, this inner product is also it's a generalization of a scalar product. That means that if these two vectors, if this bra and this ket are orthogonal, then this has to be 0. I can define also the other way, by the way. I can do the, so this is a bra times ket. So when you put them together, when you do this operation, you form a bracket, hence the name. So multiply a ket times a bra. That's what's called an outer product. So this is just a sneak peek. We'll see what that makes. Okay. So, this is standard algebra for space vectors. So that means that we have commutativity, associativity, null vector, we've already seen, inverse element, closure, identity, and so on. Okay, so we can define, like we do the same way with vectors, commutativity, so we can add two vectors together, so two kets together. So sometimes we can add them, we can reverse them, in this case, so psi plus phi equals phi plus psi. I can write it like this as well. This is sometimes a notation that we can see. We put them inside the ket because it's the same object. I have associativity, so chi plus psi plus phi equals chi plus phi plus psi, and so on. I can all the same way that you can do with vectors. I have the null vector, so that means that there is a vector 0 that added to any ket will give me my ket back. And I have an inverse element, so that means that I can have a ket and something that would give me the null vector. So this would be the inverse element. Well, basically is, you know, in standard vector notation is minus u. Okay, so here I would have minus phi. I have closure. Closure means that if I take any ket and I time it, you know, if I multiply by any numbers, I end up with another ket. Okay, with different norm, but same. It's also a ket. I have distributivity of that as well, and I can also have. So if I have constant times vector, then I have the product of the constants times the vector. Okay? And of course, I have the identity operator, is that this operator, or this matrix, times my ket gives me my ket again. I can go further. I can look into the bra part. So for instance, I can look into what happens if I times bra and two kets. Well, I have distributivity, so I can just do bra times ket plus bra times ket, which again can be written like this, for instance. Sometimes you may see this notation. It's the same thing. I have closure, except that now the closure is a bit different, because if I do the inner product of chi times lambda psi, that's equal lambda chi psi, okay? But if I do lambda chi psi, then because it's on the other side here, it's on the dual space, then when I take it out, then I have now a complex conjugate number, right? Because I have to have this complex conjugate property. I am in this space here. So in this space here, numbers, I have to take the complex conjugated of the numbers. Okay, so let's write this. So this is very important. Okay, so in the dual space, again, we see this idea that is not symmetrical, and that the left-hand side and the right-hand side are not the same thing. Okay? I mean, you know, you can just take it as a set of rules, you know, set by mathematicians, and you just have to follow and apply the rules. So what I'm saying here is that if I have this property, so if the number, so lambda is a number that can be a complex number, I can take it out, okay, like any number. It's the same if I were to have u times 2v, then this is equal to 2 times uv, okay? Except that when I do that here, I have the same thing, whether the 2 is associated to the u or the v. Except that now it's not the case. When it's associated to the ket, then it's the same thing. But when it's associated to the bra, then it's not the same thing. I have to take the complex conjugate to take it out. Okay? So so this is another rule that needs to be applied. Then if we carry on, we can see now that if I take the inner product of psi phi, then this would be equal to the complex conjugate of phi psi, right? Which is also the Dagger operation in this case, because the transpose is the same. The transpose in this particular case is the same operation. What changes though is the star. Remember, I told you that UV times VU usually is the same, except that here UV times VU is not the same. You have to have the complex conjugate to go from one to the other. So now you can combine these two properties and end up with this. So I'll let you look into that. You can also do the Dagger operation on lambda phi. So that would be lambda star times the bra, and so on and so forth. So we have this property and therefore this property because we are on the bra side. Here we are on the ket side, and so on. And of course, I can do one more property. I can have the normalization. So I can norm a vector, and I can normalize it. I can always do that. So that's true in Euclidean space. Is also true here. And finally, there's another property that we are not going to talk about at all, but I thought that I'll give it to you. Is that all of these operations can be seen as discrete operations, in the sense that we have discrete vectors, discrete quantities, but it can also be done with continuous variables. And what you would have here is that you would have a Dirac function depending on the continuous variables of the two bra in ket state. So this we will not go into, but this has a physical meaning. This is what's used in quantum mechanics to explain the position operator and the momentum operator. We need to have continuous variables. Right. So to finish that lecture 3, before probably starting a bit on lecture 4, I just want to come back to what I said before going into more later on, is that what we've seen here, so in the 3.5 part, is we've seen very, very much mathematical tools and representations. Okay, this is all of this. If I go back to all of this, it's very, very mathematically defined, okay, with some rules. Okay, just apply them and you're done. Okay, but at the end of the day, like I said, behind all of this, so for now, we need to deal with the physical side. When quantum computers will be used quite heavily in 10 years, maybe 20, maybe 100 years, I don't know. Of course, it will be like we use a computer now. I mean, most people use classical computers, and they have no idea how it works inside. They have no idea that there are transistors and semiconductors and that they have particular properties that allow the current or not dependent. They don't know that, and in fact, they don't need to know that, and that's fine. So one day, it will be the same with quantum computers, but we are still quite far from it. So at the end of the day, we are still working on the hardware. So it's still nice to go back to the physical meaning to it. And so like I said, so I already mentioned it, but this is the mathematical representation. But there is the exact counterpart, which has then a physical sense, is if we write this particular property, mathematical property, in integral properties. Because now this integral has a physical meaning. The physical meaning is that, in particular, if psi equals, so if psi equals phi, phi equals psi, then what you have here is the integral of psi star psi over d tau, where I say d tau is a volume integration. And what that means is that this quantity, psi, is what we call in quantum mechanics the wave function of the system. And it's usually a function that depends on time and space. And in quantum mechanics, the wave function is what defines any system. So a single photon, a single electron, you, me, anything can be defined by a wave function. Of course, as we said, we are not quantum, so it's not used to define us as a wave function, but there is intrinsically quantum mechanics tells you that any system you're interested in will have a wave function associated to it. And in the quantum world, that means that this integral here, for instance, what it is simply if I were to now take an electron, so really a quantum particle, when I do this integration over volume here, what I do is is the equivalent of localizing or finding the probability of having my electron, my system, at a given time in a given space. So it has a physical meaning. The physical meaning is that this integration here, which is the equivalent of that we've just seen, tells you that with this I can find what I calculate here is the probability to find my quantum particle, say my single electron, into a given space at a given time. Okay? So again, at the end of the day, like I said, and in fact, most people, that's the nice thing about it, is that colleagues from computer science, they don't actually care about this. They just use the sort of mathematical representation, and it's fine. Okay, they don't have to know what's behind it, but there is this behind it. Okay. Right. Okay. So we have a bit of time to start on the next notion. So the next notion is very important. They all are, but this one in particular, because we will see multiple qubits. So far we've dealt with single qubits, okay, just one qubit. Eventually, maybe two. We made the inner product of the two together. But now, at the end, if we have one day a quantum computer, there will be many qubits. In fact, there will be many, many, many qubits. So we need to have a formalism that can take into account the fact that we have these multiple qubits working together, and on top of it, the fact that these multiple qubits can be in parallel, can be related to each other. We said that, and can make the use of quantum mechanics. And in order to do that, what we need to do, is to understand the notion of entanglement between particles, between qubits in this case. Okay. So, here is what I'm going to cover, so not everything today. So first of all, I will start with the definition of a multiple qubit. What is a multiple qubit? Or what are multiple qubits, rather? Then I will define, again, a mathematical object, but that is extremely important, is the notion of tensor product. So we've seen inner product, we will see outer product, and there is another one, which is a tensor product, is yet another operation. Then we will see that will lead us to the so-called Hilbert space, which is the mathematical representation to understand tensor product, and in particular to understand the notion of parallelism, of quantum parallelism, which is, as I said before, which is that precisely is what provides the power of quantum information. And then I will go on to entanglement, a very important notion, how you entangle two particles together. And then I will carry on with how we do that in practice. So how do we generate 2, 3, 4, and more qubit states? So for that, I will come back to the example of photons, you will see. And then I will finish this part before going on to what I call measurements and operators, if we have them here, operators and measurements, and then quantum gates. I will come back to the physical meaning of psi that I just mentioned today. Though not too long, but I have to spend a bit of time on this. Right. So let's have a step back. So definition of multiple qubit. So we need to, first of all, we need to keep that in mind. The fact that we can multiply matrices, so that we've seen that already. So we've seen the notion of column vector, that's the ket, row line vector, that's the bra. So the bracket and dual vectors, so we've seen that. The inner product, which is this, which is the bracket operation. We've seen the notion of Hermitian matrices associated to these vectors and their product, how we can multiply them. And now we have two more mathematical objects to see. One is the tensor product, which we're going to do in this lecture 4, maybe not today. We will see it today, I think. And then the notion of outer product, which is that I showed you before, the outer product. So we have the inner product. That's the inner product. So this is the equivalent of the scalar product. But I can flip it, and I can have this operation, which we call the outer product. So that we'll see later on. Can already think of what that would do. Okay. Right, so let's talk about tensor product first. So for that, so if we want to talk about multiple qubits, then let's talk about 2 qubits. So this is the general definition of a 2-qubit state. So 2-qubit state, so what is it? It's a superposition, it's the sum of 4 terms. Again, we find this idea that if I have 2 qubits, I have 2 to the power of n output, so I have 2 to the power of 2 output, so I have 4 output. So I should have the sum of 4 terms. And indeed, I have the term 0, 0, so both qubits are in the 0 state. The term 0, 1, so one qubit is in the 0 state and the other one is in 1 state. Or 1, 0, so that's the other way around. And 1, 1, which is both qubits are in the 1 state. Okay? So for 2 qubits, okay, so 0, 0, it's 0, 0. As we will see, this is another notation. 0, 1 is 0, 1. Okay, so that would be qubit 1. And that would be qubit 2. That's 1, 0. And that's 1, 1. Okay. So, okay, of course, so this is the complete expression where we need again to have a normalized state, but let's keep it that way. So I can define now 4 coefficients. So I call them alpha 0, 0, alpha 0, 1, alpha 1, 0, and alpha 1, 1. Again, so this is the equivalent of the alpha beta, and these 4 coefficients are complex numbers again. There is one way, so before I forget, so there is one way of writing it in order to write the 2 qubits and then more qubits. And the way to write it is to link it to binary. So so imagine that this is a 2-bit binary. So if I have a 2-bit binary, in order you have 0, so that's 0, 0. Then you have 1. So this would be the way to write it. So 1 is 2 to the power, so 1 times 2 to the power of 0. Then you have 2. So the 1 is on the other one, so it's 1 times 2 to the power of 1 times 0. And then you have 1, 1. So both together for 2 to the power of 1 and 2 to the power of 0. Okay? So that's the way to remember it, is we put first the lowest, 0, 0, then 0, 1, 1, 0, 1, 1. Okay, so 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, and 1, 1. And if I were to have 3, as we will see, it'd be the same. So I start with this, 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 and then this, and then so on and so forth. Binary order. Okay, so now what I observe is that what I have is actually a so-called 4-state vector or 4-dimensional vector, because I've got 4 parts. So I can write it like this. Okay, I can write it as being alpha 0, 0, alpha 0, 1, alpha 1, 0, and alpha 1, 1. Or in other words, I can write it as a superposition of 4 states that would be the basis states. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Okay, with the coefficients. So this is a 2-qubit state. Okay, if I want to represent a 2-qubit state, the most general 2-qubit state, that's what it would look like. I can do 3. So then in this case, I have 2 to the power of 3. So I've got 8 components. So 0, 0, 0, 0, 0, 1, 0, 1, 1, and so on and so forth until 1, 1, 1. I would have 8 coefficients, all potentially different, all complex numbers, yes. And the most general state would look like this, where I would have 1, 0, 0, 0, 0, 0, 0. I would have alpha 0, 0, 1, 0, 0, plus the second one, 0, 1, 0, 0, 0, and so on and so forth. Okay, so the exact equivalent of this, but now with 8 components. So already we see, we come back to the idea that for 1 qubit, I have 2 states. For 2 qubits, 4. For 3, 8, and so on. So for 1 qubit, I've got 2 states, 2-state vector, sorry. For 2 qubits, I've got a 4-state vector. For 3 qubits, I have an 8-state vector. That's this one. Sorry, this one. And for n qubits, I would have 2 to the power of n state vector. So again, we go back to the idea that the computing power is exponentially growing with the number of qubits. Okay, this is pretty clear here. If I were to write for 4 qubits, then I would have a line with 16 coefficients, and so on and so forth. Now, how do we, and we will finish with that notion, so just to introduce the notion, so how do we now put together 2 qubits? So there has to be a specific operation in order to go from this to this to this. Because effectively what we do is we increase the space, right? So we go from so if we talk about matrix, we go from a 2x2 matrix space to a 4x4, to an 8x8, and so on and so forth. And this operation can be done and has to be done so it's a mathematical operation which we call the tensor product, which is basically an operation. So in math, we usually define it with this cross with the circle around. So if you want to remember it, it's the X-Men sign. And so that cross, so the way we use it is we say, okay, I start with 2 qubits, so psi, phi and psi. Okay, so they define like this. So now I go back to, qubits. I've got 0, 1, 0, 1. And then I do this operation. So I can write this operation into columns. So now I've got columns, by the way. This is not broad. These are 2 columns because I remain in the same space. So tensor product makes me go from the same space. I'm still in a ket space because I go from a 2D vector here to a 2-state vector to a 4-state vector. But it's still a vector. Sorry, a column. And so what it looks like is I start with alpha 0, alpha 1, beta 0, beta 1. And I end up, so therefore, with a 4-state vector, a 4-state column, with alpha 0, beta 0, alpha 0, beta 1, and so on. The way to know how you do this is what you do is you take each coefficient, so alpha 0, alpha 1, you put them here, and you multiply by the vector column of the second one each. And you end up with 1 term, 2 term, 3 terms, 4 terms. And you end up with this. Okay? So that's one way of doing it. Another way of doing it is actually that this tensor product can be seen as a multiplication operator. The only thing is you need to, when you do multiplication operators, you need to go from this notation to this notation. But if you do that, and this you can, this is equivalent to that. If you do that, then you can just simply say, well, I take my first vector, my first ket, I multiply by my second ket. So this can be seen as a standard multiplication or scalar product between vectors. So if I do that, I've got 4 terms. So this times this, plus this times this, plus this times this, plus this times this. So here are the 4 terms. I've got the 0, 0, 0, 1, 1, 0, 1, 1 notation like this, which we said can be, for simplification, be written like this. And I end up with my 4-state vector for 2 qubits. Okay? So this is a notation. So this is equivalent to this. Sometimes it's also written this, 0, 1, but it's all the same. So you can do it for 2, for 3, for as many as you want. Okay? Right. And we can do it for 3 qubits. So we will apply the same rules. So phi times psi times chi. So that would be all of those products. So first of all, we can do it with these 2. We've seen how to do that. And then we do it with this one, except that now we've got this times this vector, and then this times this vector, and then this times this vector, and then this time. And then we end up with an 8-column vector. Okay? Right. So I think with this, we'll stop here. So next week, we will carry on onto the notion of multiple qubits, and we will see the notion of entanglement. We're already almost there. We have all the ingredients to see that, and then we'll move on to operations and gates eventually. So with this, I thank you, and I see you next week. Thank you.